after realizing that I had just given you all the answers to this, I decided to cut myself off. So see if you can't answer these three questions without looking at your notes or looking at the previous video. So if I leave the battery or the cell connected for a very long time, what do you think is going to happen? What's the purpose of the salt bridge? Once the battery dies, how can you recharge it? Or could you recharge it? So let's start with the first one. If I leave it connected for a very long time, what did I say? I said that you can see in this picture here that I am losing more and more of my zinc. So my zinc is going to either break or fully dissolve. And then what's happening on this side? Well, I'm using up more and more of the copper ions. So what's going to happen there? My copper 2 plus can run out. So both B and C are correct for that. And then what's the purpose of the salt bridge? Well, that is to equalize the concentrations of the ions in the solution. So to help maintain the balance so they're both neutral solutions. Can I charge the battery? That one actually didn't give you the answer to. I kind of hinted at it. What would happen if I connected this darn thing in reverse? So in other words, if I forced electrons to go from one side to the other, well, what would happen there is then my zinc 2 plus would be attracted and start building up on the electrode on that side. And the copper 2 plus then would start getting smaller and smaller, get more copper 2 plus into the solution, and the size of that electrode would decrease. So I'd have to force it to happen, but it's the same thing you do when you look at your cell phone or your laptop or whatever you're using and you say, the battery's low, it's screaming at me, I only have 3%, I must plug it back in. So when you plug it in, you're forcing things to go in their not spontaneous direction. When I just let things run, they're going in their spontaneous direction. The thing that is most energetically favorable for both the electrodes, or for both the anode and the cathode, is what's going to happen. So now, how do we actually describe this? If I want to write these things out, we have what we call the half cell oxidation and reduction, this kind of cell diagram thing. And there's a few important components here. And all I ever tell people is just, start off with figure out which one is your oxidation side. So oxidation is loss of electrons. Reduction is gain. So I just look at and see which one is losing electrons and write that as this should be whatever the solid is. Then the next thing in is the ion it forms. In this case, it was Zn2 plus. That's a 2. And then this thing here, we use these two lines. That's the salt bridge. That's all. And then we're going to have the same pattern. On the outside here is going to be the thing that's gaining electrons, and on the inside would be its aqueous solution. So in this case, copper 2 plus. So here would be copper, and here would be zinc. As far as a way to remember that, you go from the oxidation to the reduction side. So lower in the alphabet to higher in the alphabet, kind of like in a numerical order, if you will. Going element P, Q, R. Yeah. So O to R, if that helps, or make a note. But what we can do in this shorthand is really communicate what's going on. If I wanted to write this, then I say, okay, oxidation, so this is my loss. That means I'm going to have this Zn solid going to Zn2 plus 2 electrons. And then I can go over to my reduction reaction and say, okay, that is gain. So copper solid plus 2 electrons. Oops, what am I doing? That's why that was not working out in my head. Going back. Cu2 plus 2 electrons is going to go to solid copper. And in that way, I can write my actual chemical reaction for the overall arching what's happening in my solution question. So the handiness of this is it helps communicate our half reactions and what's happening. And then from there, what you're going to see is we can do some math with that because we have some tables that give us some interesting information. So go ahead and write down the reactions that you have going on in these two solutions, and then come on back. So we have 1 molar of each. We have a nice even balance of concentrations. And let's see, what do I have going on here? Well, we can see our little salt bridge. So we have a place for our ions to come and go. I'm going from my solid copper. So I'm going from copper, and then I'm losing electrons to form, let's see, 2 electrons to form Cu2+. So I have that one. Oxidation is loss. Reduction is gain. For my solutions, here's my salt bridge. What do I have? I start off with my O, so this would be my copper solid. And then the single line for what's happening, what is it going to, is going to Cu2+. What am I doing? Oh my word, I need to drink more coffee. Cu2+ in the aqueous solution. And on this side, I'm making more solid, so I'm going to go from my Ag plus an electron to form my solid silver. Again, my ions go next to the cell, the salt bridge, and then what lives on the outside is my solid itself. So these are my electrodes. Oxidation is loss, and reduction is gain. So ox, red ox, and let's take a look at the little memory mnemonic. There we go. Actually, I want this one. Ox, red cat. I'm not good at mnemonics. So the anode, ox is the oxidation. So this is my anode. Whoops, wrong page. It's my anode. And this is my cathode. Or as I was told, the little memory trick, cat ions are positive, right? So what am I doing? I'm sucking cat ions out of solution in this one, and I'm throwing them into solution on this side, so I have my negative electrons coming up, and anode would be negatively charged, cathode would be positively charged. It's being attracted to that positive charge. So this one here, then my anode is my Cu2+, and this is my cathode, whichever one you prefer. That should be an E. There we go. So now pause this and come back and write half reactions or cell diagrams. So for the first one, you're going to want to do your half reactions and then a full reaction, and for the other two, do your cell diagrams. Okay, so now that you're back, what did I say? We go from our anode, far left, to our cathode. So here's my anode, and here's my cathode. Ox, oxidation is loss, reduction is gain. So for my cadmium, what would I have? I'm losing electrons, so Cd, solid. going to CD2 plus, aqueous, plus 2 electrons. And then my other reaction is going to be my Ni2 plus. So reduction is gain. I'm gaining 2 electrons. Aqueous, plus 2 electrons. That's an E, going to my solid. I don't know why my brain is not functioning this morning. That's not a C, that's an S. So I guess another way you can look at this is that I'm starting off, this is the one I'm starting off with a solid on, and I'm losing electrons. And then as I'm coming along, I'm gaining electrons in the other beaker to form my next solid. It's probably an easier way to look at that. And then my overall reaction for this then is just kind of combining those two, that I'll have Ni2 plus. I really need to not do these in the morning. Ni2 plus aqueous, plus my cadmium solid. And what's that going to form? I'm going to get my CD2 plus solid plus my solid nickel. There we go. Now for this one, we want to know what is gaining and what is losing. So I have 2Cr, 2Cr3 plus. Oh my word. I can hear my little dog wandering around. She wants breakfast. 2Cr3 plus. What am I going to do? I'm going to gain 3 electrons and then form a solid. And the other one is I'm going to start with solid. I start with my cation plus 2 electrons going to solid zinc. That should be an N. So oxidation is loss, reduction is gain. And what did I just do? I wrote this thing in reverse. That's not helpful. Zn solid. Notice I'm not balancing it, because right now all I'm doing is looking to make sure I keep straight who is being oxidized and who's being reduced. So my Zn solid is now going to form. There we go. Zn2 plus 2 electrons. Cool. So this is my oxidation. This is my reduction. Or going off of just kind of thinking about what's happening, then I'm going to have my zinc solid is my wet. It's going to be my anode. Going to Zn2 plus. Here's my salt bridge. Then what ions am I starting with? I'm starting with my chromium ions, Cr3 plus, and that's coming from my solid chromium. Let's do our phase labels. Aqueous. There we have it. And again, here's my anode and my cathode. All right, so for my aluminum, let's see what I have going on here. I have my 2Al. I'm going to be consistent, just not worrying about balancing it right now. Al solid. There we go. Going to, let's see, it's going to form a positive cation, so I am losing 3 electrons. And then the other one, I'm starting with H plus. What am I doing? I'm gaining an electron. I'm forming, whoops, H2. So what can we tell from that? That's actually going to be, if I wanted to balance it out, you can see I have the 6 going to 3. So what does this mean? I'm gaining 6 electrons here. And that's why the 2 then, 2 times this whole gosh darn thing, gives me those 3 electrons. So for oxidation reduction, what do I have going on here? Oxidation is loss. This is my oxidized side, and this is my reduction side. So my oxidized side goes on the outside. I'm starting with that solid, and then it's going to go into its ions. And here's my salt bridge. And then what's happening, I'm going to pick up those ions in solution. Aqueous. going to gas. Whoops, G. Nice. So by writing our half reactions, that tells us exactly what's going on in our beakers.